The mathematical inequality that unlocks quantum reality. Explore how a simple formula revolutionizes our understanding of the subatomic world. I'm excited to introduce a new playlist covering the appendix of this book here. As linear algebra is a fundamental topic in the scientific community, if this interests you, be sure to hit the subscribe button for more. So the problem of interest today is problem 8.5, which is to prove the Schwarz inequality given by equation A.27, stated here, which says that the product, or rather that the overlap of two vectors in their inner product squared is always less than the lengths of the two vectors themselves multiplied together. Visually, this represents something like this, where we're talking about lengths and areas being multiplied, and we see that the area of ACBD down here is less than this up here, okay? Now, this of course comes as a little weirdness when we're talking about vectors, but this is from a article with a visual proof without words, which I'll link in the description for your further reading. Now, this problem also gave us a hint. And the hint was to let a vector gamma be defined by some other vector beta where we're minusing off. So it kind of looks like the Gram-Schmidt process where we're orthogonalizing everything, where we're taking the projection alpha beta over its magnitude and then aligning it with alpha. Now, of course, there's several ways to do this. And for the Patreons, I have another proof of this that didn't involve this setup, but nonetheless, something that's still important to you. That being said, we also need to use the fact that the inner product of two vectors is always greater than or equal to 0, only equaling 0 when we have a 0 vector. Okay, because every geometric vector has to have a length, so that makes sense. Now, the Schwarz inequality is a fundamental principle in quantum mechanics, which is why we're covering it, and it governs the inner products of quantum states. This provides a mathematical framework for understanding the relationships between different quantum states and their probabilities. Of course, one of the most important applications of the Schwarz inequality in quantum mechanics is in deriving the uncertainties or understanding the Heisenberg uncertainty principle. Of course, we saw that we had to have uncertainty which was less than or equal to the product of sigma operator, so that makes sense in this application. So with this background, let's go ahead and see how we prove this. So to start the proof, we need to take the inner product of gamma with itself. Now, it's going to be a little cumbersome, so let's be aware of this. So in taking the product of gamma with itself, I purposely color-coded it to know which part we're plugging in. So this gamma, we're just going to leave alone for now, and we'll use this as an artifact later with the given hint. Now the blue gamma, we're going to substitute in the hint definition of the vector, as stated here and underbraced here. That being said, thanks to equation A.21, we know we can distribute this into here and maintain two other inner products. Remember that this inner product is a number, this inner product is just a number, so these are scalars in comparison to the vector ket alpha. So when I multiply and distribute in gamma, which thankfully because of vector space axioms we know we can, we see we get two new inner products, gamma beta and gamma alpha. As a result, we can investigate what happens to this thing independently and this thing independently instead of taking gamma gamma with both of the blue definitions and distributing them out like that. Taking it piece by piece is a little bit easier to handle, and we get to see a little more intricacies of each step. That being said, the first step in this is to find out what gamma beta is. Now, to make our lives easier, equation A.19 tells us that by taking the conjugate here, we can switch the order of the things inside the inner product. Okay, fair enough. That gives us beta on the left-hand side in the bra and gamma on the right-hand side in the ket. That's fine. What this allows us to do now is use the gamma in the blue definition up here and distribute again like we would have anyways. Now, mind you, this would have happened regardless of had we just done a double gamma here. But again, taking it part by part makes it a little easier to dive into each part. So here, the beta gets distributed into here. This is the gamma from the hint. Distributivity holds because of A.21, thankfully. And we see that we end up with the beta on beta, and we still have an alpha beta here and alpha alpha here. But note that this alpha beta and beta alpha are very similar to one another, and by utilizing the A.19 formula here, we can go ahead and rewrite this and make our lives easy. So keep everything the same from this section all the way through, and just switch the alpha beta here, but with the complex conjugate. What this complex conjugate allows us to do is to take this thing, multiply it to this thing, which if you remember going back from quantum mechanics, psi star psi became the magnitude psi squared. So anytime I have a thing with its conjugate multiplied, I can put that as a magnitude squared and I'm good to go. Now that I'm in a magnitude squared, out beta beta multiplied by each other, that's going to come out to a real number because it's just the length of beta. Alpha alpha, that's going to come out to a real number, and the magnitude squared comes out to a real number. So all of these things turn out to be a real number. As a result, this complex conjugate doesn't do anything in terms of our sign switching, so we're good to go to rewrite this as gamma beta or beta gamma, thanks to this result here. Okay, and that's going to be important to us because when we go to plug in gamma beta here, we can just plug in the beta gamma and use this result, which we'll see in due time. So now we still need to do the other side or the other inner product, which was gamma and alpha. Utilizing the same protocol, A.19, take the complex conjugate, give us alpha gamma, use the gamma definition from the hint. Now we can distribute that in. Now, upon distributing, we get alpha beta, and then we see that we get alpha alpha here, this to this to that. Easy enough. But we see that the inner product of alpha alpha, they cancel. Beautiful. Then we see in simplifying, we get alpha beta minus each other. Cool, we get a 0. And this is why the author gave us the hint, because this turned this inner product in kind of a reverse engineering manner to equal 0 here. As a result, when we go back to our first inner product statement of proof, we can go ahead and plug this 0 in here and put the reverse order of beta gamma in here, so we're fine. Of course, the complex conjugate doesn't matter, so we could switch these at no cost. So the green turns to beta gamma here, and now we could use the result that we saw last time, which is what I foreshadowed earlier, and that gives us this. Now we're in a very good position to make use of another equation and make the inequality come true. So from equation A.20, we know that the inner product of two vectors gamma gamma is greater than or equal to 0 for all gamma that are not the 0 vector. Thus, we see that we have gamma gamma here is equal to beta times beta, or the inner product of beta beta, the magnitude squared alpha alpha, and all of that has to be greater than or equal to 0 thanks to this thing here. From here, we just minus or add this thing over across the inequality. Now we can multiply this over, and upon multiplying it over, we get the desired result, or the Schwarz inequality, which once again states that the inner product alpha beta, which is the overlap of the two vectors, square that, is less than or equal to the length of alpha and the length of beta multiplied together. Very, very cool. Now, for the patrons, the Cauchy-Schwarz inequality is another crucial inequality in this realm, and I go ahead and state and prove it using a different method from a more linear algebra context, but you'll have that in the PDF on Patreon. That being said, there was another proof without words given here, which I thought this one was, kind of reminded me of engineering and, moment diagrams, things like that. But it's just a geometric process where we're cutting things into triangles here. So this area got moved here, this area got moved here. So we're keeping equivalent areas here. Then we're projecting them up as we see here. And then we end up with another product. And then from here, the author goes ahead and shows the inequality once again. So in math and physics, there's a million different ways to get the right answer, quote, right answer, but the way that you can be creative with it is really fascinating. So I have two of these papers will be linked below for you to read or investigate, because these are really cool applications that are not intuitive at first, but then once you see it, that light bulb goes off and you're really happy you did see it. All right, so that was a pretty quick video, but nonetheless a very powerful result. And if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And for anyone else who is interested in joining or supporting the channel, you can join our Patreon community and just do that by accessing the link below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.